number 1. Op-amp is ideal and all resistors are 1 ohm. The output voltage is. This output voltage V out is to be identified. Op-amp is connected in negative feedback mode, hence V plus equal to V minus is valid. V plus can be easily identified. Two sources between equal resistors divides equally, so 1 plus 1 divided by 2, 2 by 2 plus 1 volt. My V minus also should be positive 1 volt. Both ends are at same potential, hence there is no current flow through the resistance. There is no input current, there is no current coming from the op-amp, so this current also equal to 0, implies voltage across this resistance also equal to 0. This voltage with respect to ground is positive 1. I have 0 drop here, implies this node voltage also positive 1 with respect to ground, hence V out equal to positive 1. Question number 2. Assume the op-amp is idle and all resistors are 2 ohms. Obtain the output current in amperes supplied by the op-amp. All resistors are 2 ohms. Op-amp is connected in negative feedback mode, hence V plus equal to V minus is valid. V plus can be easily identified. I have two sources, minus 3 and plus 1 divides equally between the resistors. So minus 3 plus 1 divided by 2, minus 2 by 2, minus 1 volt. So V plus equal to minus 1 volt with respect to ground. That demands a V minus of minus 1 volt with respect to ground. These two nodes are connected together, so my output is also minus 1 volt with respect to ground. The current flowing through the resistance is nothing but 1 minus minus 1 divided by 2. That's equal to 2 by 2. That's equal to 1 ampere. So the load resistance towards up is nothing but this potential is 0. So the current flowing up is nothing but 0 minus minus 1 by 2. That's equal to 1 by 2 amperes. So 1 by 2 amps flows up. 1 ampere comes to this branch. So at node these two currents are meeting. So 1 by 2 plus 1, 1.5 amperes flows into the output side of the op-amp. Hence, actually the op-amp sink a current of 1.5 amperes implies the current supplied by the op-amp is minus 1.5 amperes. Question number 3. Assume op-amp is ideal and all resistors are 1 ohm. Obtain the output voltage of the op-amp in volts. This V out is to be identified. All resistors are having a value of 1 ohms. Op-amp is connected in negative feedback mode, hence V plus equal to V minus is valid. V plus can be easily identified. 1 volt source divides equally between 1 ohm resistors. This value will be 1 by 2 volt. My V minus also will be at 1 by 2 volt level with respect to ground. This unknown voltage V out is to be identified. At V minus node I have 3 branches. This is my V out current. Let me mark it as I1. The incoming current I2. Another incoming current I3. There is no current into the op-amp. There is no current from the op-amp. Hence the currents I1 plus I2 plus I3 should be equal to 0. KCL at V minus node. I1 is nothing but V out minus 1 by 2 divided by 1 ohm plus I2 is nothing but 1 minus 1 by 2 by 1 ohms plus I3 is nothing but minus 1 minus 1 by 2 divided by 1 ohm should be equal to 0. That implies V out minus 1 by 2 plus 1 by 2 minus 3 by 2 equal to 0. Implies V out is equal to positive 1 point. Question number 4. Assume op-amp is ideal and all resistors are equal. Find the value of Vx such that output voltage of the op-amp is positive 2 volts. All resistors are equal and V out is given as positive 2 volts. Hence I have positive 2 volts here. Op-amp is connected to negative feedback mode, hence V plus equal to V minus is valid. V plus can be easily identified. V plus is equal to two sources minus 3 and Vx divides equally. So minus 3 plus Vx divided by 2. My V minus can be easily identified using these two source and a minus 2 source between equal resistors. So V minus is equal to minus 2 plus 2 divided by 2 divides equally will give me 0. V plus should be equal to V minus. V plus is nothing but minus 3 plus Vx divided by 2. That should be positive 3 volts. Question number 5. In the circuit, assume the op-amp is ideal and all resistors are 2 ohms. The output voltage of the op-amp is. All resistors are. Op-amp is connected in negative feedback mode, hence V plus equal to V minus is valid. This voltage is to be identified with respect to ground. V plus can be easily identified. 1 ampere flows through this because there is no input current to the op-amp. So voltage across this 2 is 2 multiplied by 1, that is 2 volts. I am expecting my V minus also positive 2 volts. That implies with respect to ground, I will have a 2 volts at my V minus. 2 ampere current flows through this, 2 ampere flows through this, develops a voltage of 4 volts in the given polarity. To identify the unknown V out, I'm writing Kirchhoff current law around the, Kirchhoff voltage law around the loop. I'm starting from 0, negative positive, positive V out, negative positive, positive 4, positive negative minus 2. I have reached here. I was started from here. So it's a closed loop equal to 0. Implies V out is equal to minus 2 volt. Question number 6. Assume the op-amp is ideal and all resistors are equal. Obtain the output voltage of the op-amp in volts. This V out is to be identified. Op-amp is connected in negative feedback mode, hence V plus equal to V minus is valid. V plus can be easily identified. Minus 1 volts divides equally. Equal resistors equally between the resistors will give me minus 1 by 2 volts. That demands a V minus also at minus 1 by 2 volts. This node voltage is V out. This node voltage is positive 2 with respect to ground. Hence V minus can be equated to V out and positive 2 divides equally between equal resistors. So V out plus 2 divided by 2, and that should be equal to Y. V plus is given as minus 1 by 2 volts. Implies V out is equal to minus 1 minus 2, that's equal to minus 3 volts. Hence V out equal to minus 3 volts. Question number 7. The op-amp in the circuit shown below is ideal. All resistors are 1 ohm. Obtain the output voltage is connected in negative feedback mode. Hence V plus equal to V minus is valid. V plus can be easily identified. Two sources divides equally between resistors. So my V plus is nothing but minus 3 plus 1 divided by 2. That's equal to minus 1 volt. So this potential is minus 1 volt. I'm expecting same minus 1 volt at my V minus. This node voltage is nothing but V out. So plus 1 and V out divides equally between resistors. So my V minus is nothing but 1 plus V out by 2. That should be equal to my V plus, that's equal to minus 1 volt. Hence V out equal to minus 2 minus 1, that's equal to minus 3 volts. Question number 8. All resistors in the following circuit are equal. Obtain the output current supplied by the op-amp. Assume ideal op-amp. Op-amp is connected in negative feedback mode, hence V plus equal to V minus is valid. The 1 ampere current flows through like this. Voltage of let us say R volts. This output is also equal to R volts. Because V plus equal to V minus is valid, this is also at R volts. These two nodes are connected together, so my V out is also equal to R volts. Hence the current flowing towards down is nothing but R minus 0 by R, that is 1 amperes. This 2 ampere circulate through this. There is no current into the op-amp. There is no current from the op-amp. So that 2 amps flows through this. 2 amps flows through this. So 2 amps come in. 1 ampere leaves. Implies another 1 ampere should flow into the op-amp. Hence, actually the op-amp sink a current of 1 ampere. Hence, the current supplied by the op-amp is nothing but minus 1 amperes in this direction. Question number 9. The op-amp is ideal. The output voltage of the op-amp is in volt is. This voltage V out is evaluated with respect to ground. Op-amp is connected in negative feedback mode, hence V plus equal to V minus. So V plus can be easily obtained minus 4 by 2 minus 2 volts. This potential is at minus 2 volts. Equal resistors, no current flows through 2 ohm resistance, hence there is no current flows through 6 ohm resistance, there is no drop across 6 ohm resistance. This is at minus 2 with respect to ground, 0 drop. This node voltage also will be equal to minus 2 volts with respect to ground. Question number 10. Assume the op-amp is ideal, obtain the output voltage. This output voltage V out is to be evaluated. Op-amp is connected negative feedback mode, hence V plus equal to V minus is valid. This node I have my minus 3 volts connected like this. So my V plus is nothing but negative positive 2, negative positive 3, 2 plus 3 5, so minus 5 volts with respect to ground. I am expecting same minus 5 at V minus. These two nodes are connected together, so V out is also equal to minus 5 volt. Question number 11. The output voltage of the op-amp is. This V out is to be identified. Op-amp is connected in negative feedback mode, hence V plus equal to V minus is valid. V plus can be easily identified. 3 volts divides equally, so this is 3 by 2 volts. I am expecting same 3 by 2 volts at my V minus. This node voltage is V out, this is at ground, hence V minus can be written as V out divides between 2 and 6, so V out multiplied by 2 divided by 2 plus 6, 8, and that should be equal to 3 by 2. Implies V out is nothing but 24 divided by 4, that's equal to positive 6 volts. So question number 12. In the circuit shown, op-amp is ideal. The output voltage of the op-amp in volts is. This voltage V out is to be identified with respect to ground. Op-amp is connected in negative feedback mode, hence V plus equal to V minus is valid. V plus can be easily identified. 3 volts divides equally, so 3 by 2 volts. I am expecting same 3 by 2 volts at my V minus. Implies I have a 3 by 2 volts connected like this with respect to ground, 3 by 2 volts. 1 ampere current flows through this because there is no input current, there is no current from the op-amp. So that develops a voltage of 6 volts in the given polarity. This V out is unknown. For identifying V out, I am writing a KVL around the loop. I am starting from here, negative to positive, hence positive V out, plus minus, so minus 6. I have reached here, then positive to negative, 3 by 2 implies minus 3 by 2, that's equal to 0. Starting from ground, ending at ground, closed loop equal to 0, implies V out is equal to 6 plus 1.5 positive 7.5 volts. Question number 13. Given the op-amp is ideal, the output voltage in volts is. This V out is to be identified with respect to ground. Op-amp is connected in negative feedback mode, hence V plus equal to V minus is valid. 2 amperes circulate like this, develops a voltage of plus minus 6 volts. That implies my V plus with respect to ground is minus 6 volts. V plus equal to V minus demands a minus 6 volts at my V minus. 1 ampere circulates through this. There is no input current, there is no current from the op-amp, hence that 1 ampere flows through 6 ohm, develops a voltage of 6 volts in the given polarity. At V minus, I have a minus 6 volts connected like this. So to identify the unknown voltage V out, I am writing KVL around the loop. I am starting from here, I will end here. So I am starting from here, negative, positive, V out, plus minus, minus 6, then negative, positive, plus 6 equal to 0. Implies V out is equal to 0 volt. Hence this V out equal to 0 volts. Question number 14. Opamp is ideal. The output current supplied by the opamp in ampere is. The op-amp is connected in negative feedback mode, hence V plus equal to V minus is valid. V plus can be easily identified. 2 ampere circulate like this, develops a 6 volts. This is at minus 6 volts. Implies my V minus is also at minus 6. These two nodes are connected together, hence my V out is also at minus 6 volts, minus 6 volts. The current flowing towards up is nothing but this is at 0 potential, this is at minus 6 volts, so 0 minus minus 6 divided by 3, 6 by 3, positive 2 ampere comes up, 2 ampere towards up. And the same 1 ampere flows through this branch. There is no input current, there is no current from the op-amp. Hence 1 ampere flows like this. 1 ampere leaves the node, 2 amps comes and 1 ampere leaves, implies 1 ampere should flow into the op-amp. Hence actually the op-amp sink a current of 1 ampere, hence the current supplied by the op-amp is minus 1 ampere in the given direction. Question number 15. In the given circuit, op-amp is ideal if V1 equal to V2 equal to plus 1 volt, obtain V out. V2 positive 1 volt, V1 also equal to plus 1 volt. Op-amp is connected in negative feedback mode, hence V plus equal to V minus is valid. Both potentials are equal. Hence, there is no current flow through R, there is no current into the op-amp, there is no current from the op-amp, hence current flowing through 2R is also 0 amperes. No drop across 2R, 0 volts. This is my positive 1 with respect to ground, minus the drop 0 will give me V out. So 1 minus 0, this also will be at positive 1 volt. Question number 16. Let the op-amp is ideal in the circuit shown. Identify the value of R in ohm to ensure V out equal to 2 times of V1 minus V2. V out is equal to 2 times V1 minus V2 implies output contains only the differential term Vd, and this will be my AD. My AC component and VC components are 0. AC, VC common mode components are 0. This happens if a difference amplifier is balanced, implies the product 1 into 2 should be equal to 1 into R, implies R equal to 2 ohms. Question number 17. Let the op-amp is ideal in the circuit shown below. Identify the condition to ensure V out equal to Vi in the circuit. This is a simple non-inverting amplifier. Its V out is nothing but Vi multiplied by 1 plus feedback resistance R2 divided by R1. V out equal to Vi when R2 by R1 equal to 0. Implies the one condition is R1 equal to infinity, the other condition is R2 equal to 0 or both. Hence the right choice is all of the above. Question number 18. Assume the op-amp is ideal given R1 equal to 3 out by Vi is nothing but 1 plus R2 by R1. R2 divided by R1 is given as 3 times R2. So the voltage gain is nothing but 1 plus 1 by 3, that's equal to 4 by 3. Question number 19. The output voltage of the op-amp is. Here V plus equal to positive 1 and V minus is at 0 volts. So this is equivalent to an open loop configuration with output resistance directly connected to ground from the output node, and my positive input connected to plus 1, my negative input connected to a 0 volts. Since it is in open loop configuration, I have my V out is equal to differential gain AD multiplied by the difference in the input V plus minus V minus. V plus is 1 volt, V minus is 0, so this is positive 1. Multiplied by AD will be infinity ideally. So V out demands a positive infinity, but that is restricted by the positive supply voltage, hence the output will be at positive VCC. V plus not equal to V minus in this circuit. Because question number 20, obtain the output current supplied by the op-amp. Op-amp is connected in negative feedback mode, hence V plus equal to V minus is valid. So this potential will be at 0 volts. 1 milliampere current flows through this. 1 milli multiplied by 3 kilo will give me 3 volts in this polarity. So V out is minus 3 volts. Flowing through 1 kilo ohm is nothing but 3 minus 0 by 1k, 3 milliamps down. There is no current into the op-amp, there is no current from the op-amp, hence 1 milliampere circulates through this resistance, 1 milliampere flows through this branch. So op-amp should supply a current equal to 1 plus 3 equal to 4 milliamps. Hence the current supplied by the op-amp is 4 milliamps. Option D is correct choice. Question number 21. Consider the circuit with ideal op-amp. Obtain the output voltage in volts. This V out is to be identified with respect to ground. We have two voltages V1 and V2. Negative feedback dominates in the circuit, hence V plus equal to V minus is valid, implies this voltage will be at V1 volts. V out can be easily identified by adding drop across this resistance plus drop across this resistance. The current flowing through this is nothing but hence I should identify the current flowing through this resistance, let us say I. That current is the sum of current flowing through this resistance, let me mark it as I1, and the current flowing through this branch I2. Because there is no current into the op-amp, there is no current from the op-amp. So the output voltage V out is nothing but I1 multiplied by R plus I multiplied by R. And the value of I is nothing but I2 plus I1. So I is nothing but I2 plus I1. I2 is nothing but V1 minus V2 by R plus I1 is nothing but V1 minus 0 by R. Hence my V out is nothing but I1 multiplied by R. I1 multiplied by R is nothing but your V1 with respect to ground. So V1 plus I multiplied by R. I multiplied by R will be equal to V1 minus V2 plus V1. Hence V out is equal to 1, 2, 3, 3V1 minus V2. Hence option C is the right choice. Question number 22. Given V1 equal to minus 1 volts and V2 equal to positive 2 volts, obtain the value of V out. This V out is to be identified with respect to ground. V1 is given as minus 1 volt, V2 is given as positive 2 volts. Both op-amps are connected in negative feedback mode, hence V plus equal to V minus is valid in both cases. That implies this voltage is nothing but minus 1 volt with respect to ground. Implies the voltage is plus minus 1 volt across R. The same current flows through these resistors because there is no input current, there is no current from the op-amp. Hence, the voltage across the second resistor also having the same polarity, plus minus 1 volt. So this node voltage is nothing but negative positive 1 plus negative positive 1 implies minus 2 volts. V plus equal to V minus is valid. I am expecting a positive 2 volts at my V minus. That can be easily identified. This minus 2 and this node voltage V out divides equally between equal resistors. So my V minus should be equal to V out minus 2 divided by 2, and that should be equal to my V plus, that's equal to positive 2 volts. Implies V out equal to 4 plus 2 equal to 6 volts. Hence V out is positive 6 volts. Question number 23. Obtain the voltage gain of the circuit. The op-amp is connected in negative feedback mode, hence V plus equal to V minus is valid. That implies this potential will be at V in. Hence this drop is nothing but plus minus V in. This voltage can be easily identified. There is no current into the op-amp, there is no current from the op-amp. Hence, the current flowing through these two resistors are same. The current flowing through 1K resistance is nothing but voltage across 1K is V in divided by 1K. So current flowing through 2K is nothing but V in by 1K. That V in by 1K multiplied by 2K will give me 2 times V in across my 2K resistance. Hence, this potential is nothing but plus minus 2 plus minus 1. So plus minus 3 times V in volts. The current flowing through 3 kilo ohm, let me mark it as I. Hence, V out is nothing but I multiplied by 3K plus 3 times V in. So this V out with respect to ground is the sum of this voltage and this voltage. So V out is nothing but I multiplied by 3K plus 3 times V in. The value of I is nothing but the current flowing through this, let me mark it as I1, plus the current flowing through this, the value is I2. Current flowing through 4 kilo ohm is nothing but 3 V in minus 0 by 4. So I is nothing but 3 by 4 V in plus this branch current I2 is nothing but same current flowing through 1K, that's equal to V in by 1 kilo ohms. So my V out is nothing but I multiplied by 3K. So 3 multiplied by 3, 3 V in plus another 3 V in. So V out is nothing but 9 by 4 plus 3, 9 by 4 plus, that will give me 3 plus 3, 6. So 9 plus 6, so V out by V in is equal to 9 plus 24, 9. Hence, right choice is option C, 33 by 4. Question number 24. The power supplied by the source Vs in milliwatts is. The power supplied by any source is nothing but source voltage multiplied by the current supplied by the source, Is. Here we are having two feedbacks, both positive and negative. And my V minus can be easily identified as this V out voltage divides equally generates a V minus of V out by 2, hence 50% feedback at my V minus node. While evaluating the component of output voltage at my inputs, I should neglect the independent sources. Here I am having a Vs voltage source independent, so I have to short to ground. Under this condition, I have 1K and 1K in parallel, that's equal to 0.5K, and in series with 1K. So my V plus is nothing but V out multiplied by 0.5K divided by 1.5K. It implies V plus will be always less than V out by 2. Hence, V minus is greater than V plus. Hence, negative feedback dominates in the circuit. Hence, V plus equal to V minus is valid in the circuit. So, this current Is can be easily identified by applying KCL at this node. Prior to that, I should mark this node voltage that is same as my V minus. V minus was V out by 2, so I will get a V out by 2 here. So the current flowing in this direction is nothing but the current flowing through 1 kilo ohm, that's equal to IL, plus the current flowing through the second resistance. Let me mark it as I. So IS is nothing but IL plus I. IL is nothing but V out by 2 minus 0 by 1. So IL is nothing but V out by 2 milliamperes plus I value is nothing but V out by 2 minus V out divided by 1K. So V out by 2 minus V out, that much milliamperes. Here V out by 2 and minus V out by 2 will get cancelled, implies Is will be equal to 0. Hence the power supplied by the source is nothing but Is equal to 0 amperes. Hence power supplied will be 0. Power supplied will be 0 watts. Obtain question number 25. Obtain the value of current flowing through RL. While evaluating the current flowing through RL, I should mark the direction. So let me mark it as IL flows like this. The circuit has both feedbacks, positive and negative. Hence, I should identify which feedback is dominated in the circuit. While evaluating the amount of feedback at the input side, I should neglect the independent sources. Here it is my independent voltage source, so I should short to ground. Implies my V minus is nothing but V out divides equally between resistors. So V out equal to, V minus is equal to, so V minus is equal to V out by 2, implies 50% of feedback. 50% output is fed back to the negative input. At the positive input side, I am having R in parallel with R in series with R. So V plus, there is no current flowing through the Opamp, input side of the Opamp. There is no current coming from the input side of the Opamp. So V plus is equal to R parallel RL multiplied by V out divided by R plus R parallel RL. So V plus will be always less than V out by 2. Hence negative feedback is dominated in the circuit. Hence V plus equal to V minus is valid. So while evaluating the current IL flowing through RL, I should connect my Vs back to the circuit. So this potential is at, I have two sources now, Vs and V out. This potential is nothing but, this potential is nothing but, V minus is equal to, when Vs is present, Vs plus V out by 2. That demands a V plus also equal to Vs plus V out divided by 2. The current IL is nothing but current flowing through R, let me mark it as I, minus the current flowing through the second resistance, let me mark it as I1. So IL is nothing but I minus I1. I is nothing but, this node potential is V out, this is at Vs plus V out by 2. So V out minus V out plus Vs divided by 2 whole divided by R. That's equal to V out minus Vs divided by twice of R. The current I1 is equal to, this node voltage is Vs plus V out by 2 minus 0 divided by R. So Vs plus V out by 2R. The difference between these two is equal to IL. So IL is nothing but I minus I1. So V out minus Vs by twice of R is my I minus my Is is Vs plus V out by 2R. So V out by 2R, V out by 2R will cancel each other. Minus Vs by 2R minus Vs by 2R will add up, will give me minus Vs by R. So the current IL is nothing but minus Vs by R. Question number 26. In the circuit shown below, if RL equal to R, the voltage gain and current supplied by the op-amp are. So in this circuit, as earlier, negative feedback is dominated, hence V plus equal to V minus is valid. The current flowing through RL in this direction is nothing but minus Vs by R. If RL equal to R, the drop across this is nothing but minus plus Vs by R multiplied by R will give me Vs. So this potential with respect to ground is nothing but minus Vs. Op-amp is operating in negative feedback mode. So V plus equal to V minus. So V minus can be easily identified. I am having two sources, Vs and V out divides equally. So my V minus is nothing but V out plus Vs divided by 2. That should be equal to my minus Vs implies V out plus Vs equal to minus 2 times Vs implies V out equal to minus 3 times Vs. Hence the gain V out by Vs is nothing but minus 3. The current supplied by the op-amp can be easily identified by identifying these two branch currents. Let me mark it as I1 and I2. This I out is the current supplied by the op-amp. So I1 is nothing but the current flowing through this R. The same current flows through this resistance R. This potential is at minus Vs. So current flowing in this direction is nothing but minus Vs minus Vs by R. So minus 2 Vs by R. So this is minus 2 Vs by R I1, and I2 is nothing but V out minus I2 is equal to V out minus Vs by R. That's equal to V out plus Vs divided by R. V out is given as minus 3 times Vs. So this is equal to minus 3 Vs plus Vs. So minus 2 Vs divided by R. So minus 2 Vs divided by R. Sum of these two currents I1 plus I2 will be my I out. Hence the current supplied by the op-amp is nothing but minus 2 Vs by R plus minus 2 Vs by R minus 4 Vs by R. Hence current supplied is minus 4 Vs by R and the voltage gain is minus 3. And option A is the right choice. Question number 27. In the circuit shown below, op-amp is ideal. The output voltage in volts is. Op-amp is connected in negative feedback mode, hence V plus equal to V minus is valid. I have a current source connected like this. Source transformation, this node will be positive, then this while transforming into the voltage source. So I have 15 implies like this, 15 in series with 3 in series with 2, followed by my op-amp circuit, negative positive, grounded, feedback, resistance 3 ohms. So it's an inverting amplifier. So this node potential is nothing but minus 15 with respect to ground. The series resistance will add up, 3 plus 2 is equal to 5. So V out is nothing but the voltage gain is minus 3 divided by 5 multiplied by the input is minus 15. So that will give me minus 3 minus 3, that's equal to 9 volts. Question number 28. Given the op-amp is ideal, find the value of R such that Vout equal to 2.5 V1 minus 3 V2. Vout is given as 2.5 V1 minus 3 times V2. Op-amp is connected in negative feedback mode, hence V plus equal to V minus is valid. V plus can be easily identified as V1 divides between R, hence my V plus is equal to V1 multiplied by R divided by 3 plus R. That should be equal to my V minus due to the negative feedback. V minus can be easily identified. I have two sources, V out and V2, that divides equally between 2 and 6 ohm resistors. So my interest is about V1 and V out. So I am not considering my V2. So if V2 is 0, my V minus is nothing but V out multiplied by 2 divided by 8. Right? So my V plus equal to V minus implies V plus is V1 multiplied by R divided by 3 plus R should be equal to my V minus is nothing but 2 upon 8 multiplied by V out. So the component of V1 is nothing but 5 by 2. So I have V out is equal to 4 R divided by 3 plus R times V1. This coefficient should be equal to 5 by 2, that is 2.5. So 4 divided by 1 plus 3 by R is equal to 5 by 2. That implies 1 plus 3 by R is equal to 8 by 5. That implies 3 by R is equal to 3 by 5. Implies R is equal to 5 ohms. Question number 29. Given the op-amp is ideal and all resistors are equal, the supply voltages are plus or minus 5 volts. The values of LTP and UTP are. This belongs to a Smith trigger circuit. The feedback is positive. LTP and UTP are asked. LTP is the lowest value of Vin at which the resistor change at the output, and UTP is the highest value of Vin at which the resistor change at the output. So output can be either plus 5 or minus 5. So the value of V minus can be easily identified. Positive 1 divides equally, so this will be 1 by 2 volts. And this is my V out. That output can be either plus 5 or minus 5. If that is plus 5, I will have my V plus is equal to V in plus 5 divided by 2. If you are equating that to 1 by 2, you will have one value of V in, and that value will be equal to V in is equal to minus. If you are equating V in minus 5 by 2, that's equal to 1 by 2, you will have V in is equal to 6. V in equal to positive 6. Hence the lowest one is LTP and highest one is your UTP. LTP and UTP. Hence LTP is minus 4, UTP is plus 6. Option A is the right choice. Question number 30. Let the op-amp in the circuit shown below is ideal. Obtain the voltage gains. V plus equal to V minus is valid. So I'll have Vi here divides equally between equal resistors. I will have Vi by 2 here. And my V out is available here, and this is my Vi node. My V minus can be easily identified. V out divides between 1K and 2K, so V out multiplied by 1 divided by 1 plus 2, 3 plus Vi divides between 2 and 1, so Vi multiplied by 2 by 3, that should be equal to my Vi by 2, as 2Vi is equal to 3 by 2 Vi. Hence V out is equal to minus 0.5 Vi, implies V out by Vi equal to minus 0.5, and option B is the right choice.